So let's take a look at how the renals are going to function now. So the renals are going to function to regulate the volume composition of the fluids of the body. This includes the chemical composition as well as the pH of all the bodies. It's going to be involved with the removal of metabolic wastes, as well as homeostatic regulation of metabolites. Most of this action is going to be taking place within the functional unit of the nephron. It's going to be involved with the production of erythrocytes, the RBCs, via secretion of EPO. It's going to be involved with regulation of total peripheral resistance through the production of renin. The function of the nephron is based off of Starling's law in terms of the motion of fluids across the membrane. What's going to happen is that fluid is going to move from the glomerulus into Bowman's capsule. Within Bowman's capsule, then move into the proximal convoluted tubule, into the loop of Henle, and then into the distal convoluted tubule. The movement of fluids into Bowman's capsule to start the formation of urine is referred to as filtrate. The process of changing the concentration of the fluid within the lumen of the nephron is the process of urination. Urination is not the release of urine from the urinary bladder. Urination is the process of forming urine. It forms via osmotic gradient draws within and surrounding the nephron through a process known as the countercurrent multiplication system, in which we're going to attempt to filter and remove metabolic wastes, toxins, as well as allow for metabolites to move in and out of the plasma so as to be homeostatically regulated. In this process of homeostatic regulation, we can have a small bit of gluconeogenesis taking place through the taking of glucose metabolites and reforming it into glucose within the juxtaglomerular cells. So if we remember our anatomy of the nephron, this is what we're looking at. So we start with the movement of fluid from the afferent arteriole into the glomerulus, at which point in time we're going to have filtration of materials through the slit membranes in the glomerulus into Bowman's capsule, and then into the proximal convoluted tubule. We will then have movement of materials from the PCT, the proximal convoluted tubule, into the peritubular capillaries through passive transport, as well as small bit of active transport, very little active transport. Most of the movement here is strictly due to diffusion gradients. About 90% of all of the stuff that comes into the filtrate will be reabsorbed within the proximal convoluted tubules. At which point in time we then head into the loop of Henle, what most books will refer to as the nephronic loop. The nephronic loop, or the loop of Henle, has two distinct areas to it, the descending and ascending limb. It's at this point in time that the fluid flow within the vasculature goes in the opposite direction of the fluid flow within the nephron. And this is where we get what's referred to as the countercurrent interaction. The countercurrent interaction takes place between the loop of Henle as well as the vasorectal capillaries and peritubular capillaries that surround the nephron. We will then move into the distal convoluted tubule, where we'll get last bit of ion movement, in particular hydrogen ions, at which point in time we'll then move into the collecting duct. The collecting duct is going to start to become more and more impermeable as it moves closer to the calyx of the kidney. So we go from the collecting tubule to the collecting duct into the minor calyx and then into the major calyx as we pass through the papillary membrane. The collecting tubule and collecting duct is only going to allow for a movement of materials due to hormone regulation, and in particular antidiuretic hormone, ADH, and aldosterone. So what about the movement of materials? How are we going to be able to see what moves in and what moves out? Well, it's kind of interesting because everything that moves into the filtrate, sodium, water, potassium, glucose, proteins, urea, will go about and be reabsorbed within the filtrate through tubular reabsorptive processes. The same thing that gets put into the filtrate can also be secreted into the tubules so as to allow for normal osmotic gradients to be developed. The normal osmotic gradients is going to be controlled and regulated by bulk flow principles governed by Starling's law and Fick's law, where the total volume and concentrations is due to the relationship between the ions within the filtrate and the ions within the plasma. And it goes back to the same adage that we talked about when we talked about osmosis and osmotic movement, where we can simply state wherever water moves, so will salt. And wherever salt moves, so will water. Within the nephron, we can add one more component to that, and that is wherever waste moves, so will water. Wherever water moves, so will waste. And the waste that we're talking about is what's referred to as urea. Within the loop of Henle and the collecting duct, there is a movement of urea known as the ureic cycle that allows for urea to be reabsorbed within the medulla, within the medular region of the kidney, that allows for additional water to be held within the medulla. The movement of salt, the movement of urea out of the filtrate allows for the renal medulla, the kidney medulla, to act as a sponge for water, to hold on to water so as to control the volume and rate of Uranus being formed. So how do we determine the rate of Uranus being formed? This is where we look at what's referred to as filtration rate. Filtration rate, or glomerular filtration rate, is relatively constant. It can be changed based off of sympathetic stimulation, and it can be changed based off of cardiac shifts, change of blood flow due to metabolic demands. It could also be changed based off of total blood volume, total water volume, as well as relative hydrostatic and osmotic pressures in between the capillaries of the glomerulus and Bowman's capsule itself. Unless otherwise told, the number that we will always use in our calculations is 125 milliliters per minute or 180 liters per day. These numbers become very important when we talk about the reabsorption in the urination process, because if we do not reabsorb 99.9% of all of this fluid, we're going to have to recollect it somehow by ingesting that fluid. The filtrate is going to contain anything that was in the plasma minus some proteins at the same concentration of the plasma, because it's going to be formed via diffusion, in which we're going to form the filtrate by motion through Starling's law, which means we're going to move from a high hydrostatic pressure to a low hydrostatic pressure, or from a low osmotic draw to a high osmotic draw. There are a couple of other factors that can come into play, in particular local peripheral resistance, as well as vessel diameter on the afferent and efferent side of the glomerulus. What the filtration does is it allows us to establish the mathematical relationships of what is in the plasma versus what we see within the urine, so that we can determine clearance rates and excretion rates. Clearance rates and excretion rates are very important when it comes to doing any type of metabolic screening or examination of any type of drugs within a person. So let's take a look at the process as it relates to the formation of the filtrate. We're going to look at it based off of Starling's law principles. However, remember, there is a secondary regulation here based off of the viscosity and velocity of flow, where we are going to be able to regulate glomerular filtration based off of the vasoconstriction and vasodilatation of the afferent arteriole heading into the glomerulus, where we have a high hydrostatic pressure in the glomerular capillaries and a less hydrostatic pressure within the capsular space itself. We will also have a osmotic pressure that is lower in the capillaries than within the capsule itself, which gives us a net filtration rate out of about 10 millimeter mercury pressure. That 10 millimeter mercury pressure difference is enough to allow us to form the filtrate, which will head into the proximal convoluted tubule to eventually form the urine. So let's take a look at glomerular filtration rate and how it's going to be regulated and how that goes about allowing us to determine filtrate load, excretion rates, and clearance rates for substances. So we start with an increase of GFR. That means there's too much fluid flowing through into the glomerulus, and we want to somehow protect it. So the Jess glomerular cells will start detecting that we have too much stuff coming into circulation. This is going to cause the Jess glomerular cells to reduce the amount of nitrous oxide being produced. We're also going to downregulate nitrous oxide receptors, and we're going to reduce the rate of activation at the afferent arteriole. This reduction of nitrous oxide stimulation leads to vasoconstriction on the afferent arteriole because nitrous oxide is a nice vasodilatator. The other thing we have happening is we may have some sympathetic stimulus that can come into play that's going to change the amount of vasoconstriction that we have at the afferent arteriole. All of this feeds into an inhibitory feedback loop so as to reduce glomerular filtration rate so that we do not overload that glomerulus with too much filtrate at any point of time. So what can we determine about renal functions based off of the formation of filtrate? Well, we can determine what's referred to as filtrate load. That is how much solute of a filtrate is actually being produced that can go ahead and be cleared. We can determine the clearance rate. That is, what is the relationship between what goes out into the urine versus what we see within the plasma. And then we can determine what is the excretion rate. That is, how much is actually being released as urine. So the first thing we're going to look at is filtrate load. Filtrate load is the amount of that solute filtrate that is produced by a substance due to actions at the glomerulus, in which we have a mathematical relationship of filtrate, F, equals plasma concentration, PS, times glomerular filtration rate. This is usually given in units per minute, units per hour, or units per day. So let's take a look at an example here. So we start with 0.01 milligrams per milliliter of a substance, and we have a filtration rate of 125 milliliters per minute. Milliliters cancel out milliliters. 0.01 times 125, since we're multiplying by 0.01, we're simply going to move the decimal points forward 2 spots on 125. And so we get a filtrate load of 1.25 milligrams per milliliter. So the other thing we can look at is we can look at excretion volumes. Excretion volumes is how much actually is being released in urine. The excretion volume of any substance that's being removed is not necessarily the same amount that is being filtrate. And we'll take a look at what that is here in a second when we look at what's referred to as clearance. So when we look at excretion, we're going to use the equation of US equals V, where E is the excretion per time. US is the concentration of the substance in the urine. And V is the total volume of urine that's being produced. Now remember, this is per unit time. So depending upon how long we have for the urine collection is going to be the dictate of what our time unit happens to be. So let's go ahead and let's take a look at an example of this. So we start off with our substance P, where we have a concentration in the urine of 1 milligram per milliliter. Once again, we have 2 milliliters, so those milliliters are going to cancel each other out. When they cancel each other out, we're left with 1 times 125 or 125 milligrams. And then we simply use however long we collected as our unit time. So the last thing we can go ahead and take a look at is what's referred to as clearance. So clearance is going to be the comparison of what we see in the urine to what we actually have in the plasma. And so clearance is going to be equal to the excretion, US times V, divided by the plasma concentration, PS. Within this factor, if we know 3 of the 4, we can go ahead and we can determine the remaining factor. And that's the same for any of the other equations that we look at. If we know enough, if we're all we're doing is missing one of the factors, we can go ahead and figure out the missing factor. So let's take a look at an example here. So we're going to look at what is the actual clearance of that substance P. So the milligrams are going to cancel with the milligrams. The milliliters are going to cancel out the milliliters, which leaves us with a minute and a milliliter remaining. Now, what's going to happen is because of the way in which the math is set up, we're going to flip that milliliter in the denominator to the numerator, and we simply just multiply. And we do it just the way we did it before. And so the clearance of the substance that we happen to have is about 125 milliliters of substance P being cleared per minute. So what we're going to do now is we're going to take a look at some sample problems. So when we get to the next part of the video, please go ahead and pause it and simply practice the calculations so that you know what you're doing. In the study packet for excretory function, I've given you other sample problems to work on. Please work on those sample problems. So the first sample problem that we're going to look at, a volume of 150 milliliters, a plasma concentration of 800 milligrams per milliliter, a GFR of 240 milliliters per minute, and a urine concentration of 100 milligrams per milliliter. The next example you want to try to work on, a volume of 300 milliliters, a plasma concentration of 600 milligrams per milliliter, a GFR of 120 milliliters per minute, and a urine concentration of 150 milligrams per milliliter. The last one, a volume of 1,000 milliliters, a plasma concentration of 1,800 milligrams per milliliter, a GFR of 480 milliliters per minute, and a urine concentration of 800 milligrams per milliliter. Now, please note, none of these are actual physiological numbers. They are simple numbers that will allow you to do the math very easily in terms of doing sample examples. You will have to do much more complex mathematical equations when it comes time for examination on excretory functions. So please pause the video at this point in time and practice doing the equations.